And in life, there is many different ways to measure the same thing. We just talked about that question, and we could say it went 15 meters forward, or it went 1,500 centimeters. 15 and 1,500 are different numbers, but 15 meters and 1,500 centimeters mean the same thing. So there's lots of different ways that we measure things. Some of them are in their own system, like meters and centimeters are part of a system that we would put together. But sometimes we measure things that are part of different systems. Like, how many of you, when you think of your height, first think in feet and inches? And how many of you first think in centimeters? And how many of you know both? Okay? So, if I ask, how tall are you? 184 centimeters. How tall are you? 5'10". He must be huge compared to you. You're just 5-something, and he's 184? Does that mean he's a giant and you're like tiny, tiny, tiny? No. They're different measurements. So just like we have feet and inches and centimeters, or somebody knows how much they weigh in pounds and somebody else knows how much they weigh in kilograms, we have different measurements for angles as well. Up till now, you've only learned about degrees. But in higher level math, the angle that gets used more often is called a radian. So what is a radian? Well, if I draw this, this would be a radius. And if I made a length along the edge of my circle exactly the same length as my radius, this angle right here would be called 1 radian. So in other words, the definition of a radian is the angle when the arc length is equal to the radius. If your arc length is equal to your radius, no matter how big or how small your circle is, that is considered 1 radian. Now, to get a visual of what this is, I've got an equilateral triangle here. Well, it's a little bent, but can you imagine this is a nice equilateral triangle? What do we know about equilateral triangles? All the sides are the same, and all the angles are the same. So if this triangle is perfectly straight, we could say that each of the angles was 60 degrees. So when thinking about that, if I put this triangle on top of this circle, it would look like this. Because it would all be straight. And I would have to push this point down a little bit to bend it. Right? It would be starting like this, then I bend it, and if I bent it just right so that that other edge was curved along the edge of the circle, then I would get 1 radian. So if the angle starts at 60 degrees, when I push it down and bend it a little bit, would you agree that a fair estimate would be it would be a little bit less than 60 degrees. Now, we are in pre-calculus math, and pre-calculus math likes to be exact. When someone says, what is a radian in degrees, and you say a little less than 60, they're like, I want more exact answers. So let's figure out how we can tell what this is exactly. And the key to that is thinking about the circumference. And thinking about, as I go around the edge of the circle, that's my circumference. If I can figure out how many radiuses it takes to go around the edge of my circle, maybe I can figure out how many radians are in a circle. So I started measuring, not very accurately, but if I had a piece of string exactly the length of my radius, I could bend that string around the edge of the circle and mark 1 radius, mark another radius. And I hope that you can see, again, not very accurate, that there are 6 and a bit radiuses that go around the circle. Now you've learnt your circumference formula already. You know that circumference is 2 pi r. Have you ever realized that this is really a formula that tells you how many radiuses fit around the circle? That 2 pi, which is approximately 6.28, that's telling you there's going to be 6 and a little bit radiuses around the edge of the circle. And now we have a way of finding out exactly how many degrees are in a circle. Because if there are 2 pi radiuses in a circle, this means there are 2 pi radians in a circle. And now we have a comparison point, because you know how many degrees in a circle? 360 degrees. So we can say that 2 pi radians is equal to 360 degrees. And from this, and this is on the next page, on page 489, a little shaded thing at the top of the page, they have that listed. That 360 degrees is 2 pi radians. What about halfway around the circle? Well, if halfway around the circle is 180 degrees, does it make sense that halfway around the circle in radians would be pi? And then we can manipulate this even more. Like, for example, if I do want to find out exactly what 1 radian is, can you see that I can go from pi radians to 1 radian by dividing by pi? If I divide both sides by pi, I get 1 radian is 180 divided by pi. If I type that into my calculator, it's a little less than 60. 180 over pi is exact. 57.3 is an approximation, but is a little bit more accurate than a little less than 60. So 1 radian is about 57.3 degrees. And you're like, why would I want to use that measurement? Because that sounds like a terrible measurement to work with in degrees. But the nice thing about radians, and the reason that radians are used more in higher math, is the definition of a radian is actually based on radius and lengths on a circle. Degrees are completely arbitrary. Someone decided, let's take a circle and split it up into 360 chunks. Why 360? They could have picked 400. They could have picked 600. Why 360? Well, it might be that they like things that are circular. We have 365 days in a year, so maybe we should make the circle similar. But 365 doesn't divide nicely into 4. That would make all of our math with right angle. Can you imagine if you had to know a right angled triangle was 91.25 degrees instead of 90 degrees? So I think 360 came arbitrarily out of that because it divided nicely. But it was just arbitrary, someone choosing something. A radian is actually based on, hey, when the radius is the same as the arc length, that's 1 radian. And they found no matter how big or how small the circle is, that angle stays the same. So, we can get what 1 radian is, 180 over pi. We could also go from this one to this one. If we divided both sides by 180, we'd find out what exactly 1 degree is in radians. Here is a word that you probably forgot from grade 9, or maybe they even skipped it in grade 9. subtended. We say that an angle subtends an arc when that angle, see this angle theta cuts out that arc. We would say that the arc is subtended by the angle theta. Fancy word, you'll never use it again, but when you see it in your notes and you're confused, that's what it means. I'm not going to test you on whether you know what subtended means or not, but it is in our notes here. A central angle of 1 radian is subtended by an arc with length r. So whenever your arc length is the same as your radius, that is 1 radian. And we use circumference to figure out how to change between radians and degrees, because 360 degrees is 2 pi radians. Now, in the space beside this box, let's review what we learned yesterday. We learned a formula for arc length in degrees. That formula looked like this. It was a proportion of the circumference. And we left our formula like this because it was so nice to think of all an arc length is a percentage of your whole circumference. We can now add to this everything you do in radians, everything you do in degrees, you can also do in radians. So what's my arc length formula in radians? Well, it's still going to be, if the angle's in radians, it's still a percentage of the circle, but now instead of 360 degrees, we have 2 pi radians. Same percentage, same circumference. And again, I would argue that I like both of these formulas like this. I wouldn't simplify them, okay? Especially not the one in degrees. However, on your formula sheet, mathematicians just got so excited with the arc length one because it's simplified way too nicely. Can you see that the 2 and the pi and the 2 and the pi would cancel each other out? And became such a small and elegant formula that they left it like that. So on your formula sheet, you have the arc length formula, S equals theta r. I haven't handed out your formula sheets yet. We'll get them soon. But I might have left it as a proportion of the circumference, because then it's easy to switch back and forth between the two. Okay? This is on your formula sheet, but now you have to remember that if you're using this formula, it only works if theta's in radians. It won't work if theta's in degrees. So one of the things we have to get good at is switching back and forth, right? When you go to get your driver's license, or some of you have done that already, you might know how tall you are in feet and inches, but on your driver's license, it's going to be centimeters. So someone has to convert that. Either they convert it or they remeasure you. So we need to get good at converting back and forth between degrees and radians. At the beginning, we need to learn how to convert back and forth because you're probably not very good with radians yet. So part A. You have 170 degrees and you want to convert that to radians. And we have two formulas that are going to help us. One of them is that 1 radian is equal to 180 degrees over pi. And the other one is 1 degree is pi over 180 radians. Put radians here. And the hard part about these two formulas is they look very similar. So you have to decide which one am I going to multiply by in order to convert. Now, when we multiply something, so for example, 170 degrees, we are going to multiply this by pi over 180 to convert it to radians. Two ways that you can think about which one should I do. Some people think about it this way. They think about if I have 1 degree equals pi over 180 radians, if I multiply this side by 170 and this side by 170, I will get 170 degrees equals something. So it might make sense that I need to take the 170 and use this formula to multiply. The other way that some people think about this is really pi over 180 is pi radians over 180 degrees. And since pi radians equals 180 degrees, this fraction is really equal to 1. It's a fancy way of making something equal to 1. What happens when you multiply by 1? You don't change what it's equal to. But we have actually spent a lot of our mathematical careers multiplying by 1 and changing what something looks like. You've done it in fractions, right? When you want to get a common denominator, you might multiply by 3 over 3 to change what the fraction looks like, but it doesn't change what it's equal to. So we can convert things this way. And the way that I remember is if I want to convert to radians, I have degrees on the top here. I would need degrees on the bottom so that my degree signs cancel out and I'm left with radians. I actually find that's a very useful way for doing all sorts of conversions. You will find that you have all sorts here. Here's an example of something you can do. Do you know how many inches are in a foot? Oh, I'm out of batteries, or was it turned off the whole time? Just turned off? Okay. We'll watch it. If it starts going red, could be bad. But let's do something. How many inches are in a foot? Some of you know there are 12 inches in a foot. If you want to change 38 inches to feet, you know that there are 12 inches in a foot. This is equal to 1. If I put the inches on the bottom, they'll cancel out, and I would have to divide by 12. 38 divided by 12 will give me 3.25. So 38 inches is 3.25 feet. You can do this for money. If you travel to the United States or you travel to Europe, you're going to have to convert your money. Canadian dollars to euros, Canadian dollars to American dollars. You can find out what is one of them equal to. And then you'll know whether you need to multiply or divide. So we do this, we get 170 pi over 180. You can either leave it like this, or if you want to simplify, you can. You lose no marks in grade 12 if you don't simplify your fraction. If you simplify your fraction and make a mistake, you will lose marks. But if you don't simplify, you don't lose marks. So you could leave it as 170 pi over 180.
Can I also write 17, 18 pi?
Yes. You could also write it as a fraction of pi like that as well. Okay? Part B. Is it okay if I erase part A? Oh, it also says to the nearest hundredth, so we should go to our calculator. Okay, again, I don't know if you noticed, but the last thing I did before I moved on to another question is I reread the question to make sure I hadn't missed anything. To the nearest hundredth, this is 2.97 radians. So that means that this, 170 degrees, is almost going 3 radiuses around the edge of my circle. Okay, part B. For part B, we're actually, at this point, we're going to start with section 2, which says change negative 12 pi over 11 to degrees. Because at this point, I don't think you can picture negative 12 pi over 11 very well. But you can picture things better in degrees. That's where you're at. Eventually, we want you to be able to picture things in radians and degrees somewhat equal. So what does that mean? Well, I'm going to take negative 12 pi over 11. This is in radians. I want to cancel the radians out. So when I'm multiplying, I would multiply by 180 over pi. That makes me get rid of the radians and leaves me with the degree sign. I hope you can also see that the pi's would simplify and cancel out. And if we multiply this out, we get negative 196.4 degrees. And the reason I wanted to do that first is because the question asked you to sketch, and I think it would be easier for us to sketch in the standard position. Starts on the positive x-axis, negative 196.4, or negative 12 pi over 11. I think it's easier right now to sketch if you're thinking in degrees. Can you see that negative 196 is a little bit more than 180, 16 degrees more? So we'd have to go halfway around, plus 16 degrees more. If you were thinking in radians, you have to think that halfway around is pi, and that negative 12 pi over 11 is the same as a mixed fraction, of negative 1 and 1/11 pi. So if I was trying to think in radians, I would think this is negative 1 pi. I'm going in the negative direction. Pi is halfway around in radians. And then I need to go another 1/11 of pi. 1/11, I imagine taking this other half, dividing it into 11 equal sections, and going 1/11 of those equal sections. So this is how you would draw it if you were thinking in radians. But where we're at right now, we probably think better in degrees. So changing it first to degrees and then thinking about it is probably easier than thinking about it directly in radians. But I challenge you to try to think directly in radians as early as possible, because it's going to get you used to working with that measurement. Something interesting in this one, there is a shortcut to change from radians to degrees. If there's a pi, and that shortcut is just to change pi radians to 180 degrees. What does that mean for our question? If I had negative 12 pi over 11, I could have just taken the pi and replaced it with 180. Can you see that mathematically that's what happened? When we multiplied by 180 over pi, we were left with 180, and the pi's canceled out. So some students like to use that as a shortcut if they were changing, what's pi over 2 in degrees? They just say, oh, I'll switch the pi to 180. 180 divided by 2, 90 degrees. So pi over 2 is 90 degrees. So that shortcut is useful if there's a pi, but you can only do that shortcut if you have a pi. So for example, in part C, they want to change 7.5 radians to degrees. So I put my radians on the bottom and my degrees on the top. Type this into my calculator. .7 degrees. It must be dead. This is a terrible video. It went off again. And we didn't notice. So I'll switch